In this video, we'll examine how to do the three cases of hypothesis testing for differences in independent sample means. The first case is the predominant one. This is where the population standard deviations are unknown and unequal. The second case is where the standard deviations are unknown, but we now assume that they are equal. The last case, also the least likely, is where the standard deviations are known with no regard to them being equal or not. We'll do one problem with slight alterations to work through the three cases. The situation is that we have two samples with two different treatments for viral croup, low humidity and high humidity. The mean severity score for the low humidity group is 0.98, with the mean score for the high humidity group of 1.09. The low humidity group has a sample standard deviation of 1.22 for 46 children. The high humidity group has values of 1.1 and 46 for their standard deviation and sample size. We've been told to test at a significance level of 0.05. The claim is that both groups come from the same population, which yields the null hypothesis having both means equal, with the alternative having both means unequal. We can subtract the means to test for their difference from 0. Since the test is two-tailed, we have rejection regions in the left and right. Our first task is to calculate the degrees of freedom. If we were looking at only one sample, the degrees of freedom would be n-1, or 45 for either sample. However, with two samples, we have two options. The most simple and conservative method is to take the smaller of the degrees of freedom from both samples. The second method is more accurate, but also more difficult. First, we need to divide each sample variance by the sample size. We call the first sample's result A, and the second sample result B. Then we need to plug these values into the degrees of freedom formula. In the numerator, we add A and B and then square the result. In the denominator, we divide the square of A and B by their sample degrees of freedom and add the results. The final step is to divide the numerator result by the denominator result to get the degrees of freedom. Let's plug in our sample data. The low humidity sample variance is 1.22 squared, or 1.4884. The high humidity sample variance is 1.11 squared, or 1.2321. Recall that both sample sizes are 46. The easy answer to the degrees of freedom is to pick the smaller degrees of freedom from sample 1 or 2, which are the same at 45. The more accurate method has us calculating A and B, where the variances are divided by the sample sizes. Then we plug into the formula the values for A, B, and the sample sizes. The final result is 89.21. It is usually best to round up to the higher whole number, or 90, if we must use a table. Next, we need to calculate the standard error of the combined means. That requires us to divide each sample variance by their relevant sample size, add the results, and then take the square root of the final result. We can now calculate the test statistic, which is just the difference in the sample means minus the difference in the population means, which is 0 in this example. Then we must divide by the standard error, and in this example we get a negative 0.45232. Now, let's go ahead and get the margin of error. We need a t-score for two tails. In this problem, even though we are testing at a 5% level of significance, we are asked for a 90% confidence interval, so the relevant alpha is 10%, with 5% in each tail. Also, we have two different calculated degrees of freedom, so we look up two different t-scores. But the margins of error are almost identical. Since we have the margin of error, why don't we solve for the 90% confidence interval? The equation for a confidence interval on the difference of two means is the difference in sample means plus and minus the margin of error. Therefore, knowing that the difference in sample means is negative 0.11 and that the margin of error is 0.40842 for 45 degrees of freedom, we find that for our two samples, the 90% confidence interval is from negative 0.51842 to positive 0.29842. Since this interval includes 0, we cannot conclude that the differences in means is not 0, so we must fail to reject the null based on this interval. For 90 degrees of freedom, the interval also includes 0. Now, let's look at testing the differences with critical t-scores and p-values using the Excel template. Here's the part of the template that deals with case 1 for testing means of independent samples. All the yellow-colored cells are for you to input data. The green cells are where the template places the answers. Here we also have blue cells. These cells are the values calculated for the degrees of freedom determined by the formula. Let's see how well this template works with our data. Okay, let's input the data from our example. For the first sample, we have a mean of 0.98, a standard deviation of 1.22, and a sample size of 46. For sample 2, the same statistic values are 1.09, 1.11, and 46. Notice that at this point, the following items get automatically calculated: the A and B portions of the standard error, the degrees of freedom based on the smaller of sample sizes minus 1, the formula calculating the degrees of freedom, the sample mean differences, the population mean differences, always 0 in this template, the standard error, and the test statistic, exactly as we had calculated by hand earlier. Now, let's type in 0.05 in the test significance field. We get critical scores for a left tail, right tail, and a two-tail test for both degrees of freedom. Since we are doing a two-tail test, the two relevant critical values are 2.014103 for 45 degrees of freedom and 1.986979 for 89.208 degrees of freedom. Since our test statistic is less than either critical score, we fail to reject the null. Looking at the two-tail p-value, you see that under both degrees of freedom, we do not test less than our significance level of 5%. Again, we fail to reject the null. The last thing shown here is the calculation of the confidence interval. Plug in the significance level of 0.10 to calculate the 90% confidence interval. Notice that all the values we calculate for the relevant t-scores, margin of errors, and confidence limits match what we had calculated previously. All three methods are consistent in making us conclude to fail to reject the null, meaning that the population means do not test as being different. Now, let's look at the second portion of the template that addresses the second case where population standard deviations are unknown, but we think that they are equal. Notice there isn't a single yellow field on this portion. These fields all get calculated based on what you've inputted in the yellow cells for case 1. See how the degrees of freedom are almost exactly equal to the formula method in case 1? The pooled variance is given to you here without having to calculate it yourself. A standard error from the pooled variance is calculated, as is the test statistic. Notice that the two-tailed critical scores are almost exactly the same as for case 1. The p-values are even higher here. Finally, notice that the 90% confidence interval is even wider than for case 1, still including the value 0. Therefore, our testing conclusions remain the same. For case number 3, where the population standard deviations are known, there are two input values for the known standard deviations. Here, we just assume that the first population has a value of 1.3 and the second has a value of 1.1. From the first case values, along with the assumed population standard deviations, the needed values are automatically calculated. The critical t-scores are actually z-scores, so no degrees of freedom are needed. Again, for this example, our conclusions remain the same. There is no need to do any hand calculations with the use of the template.